All right, 11 p.m. STAT3004, STAT7304. Hello, everybody. Lesson less of us here. 13. April 2nd, Friday. Any questions? All right, so just a few administrative things. You got a message from me on via Blackboard that on Tuesdays 2 to 4 p.m. I'll have a visit hour. You can come visit me virtually, just it's not going to be structured. It's also mixed with students of the other course, Mathematics for Data Science, which is effectively a basic mathematics course, kind of first-year mathematics for data science. But there are 2 hours there. Ideally, if there are several of you asking the same question, it's good that you hear other people's questions. So try to pop up at 2, and then we'll kind of schedule it until 4. Let's see how that works anyway. I think Nicholas asked me about that. About the project. So you've seen project 1. Has anybody finished project 1 already? No? No response from the audience. Nobody's finished project 1. They're like, I'm not just I cannot see any responses, cannot see your faces, I cannot see anything. Oh, here's something.
I don't think we're all that bored, Yoni, so we haven't got it done yet.
Thank you, TJ. Okay, I got some response from TJ. Okay, he's not that bored, which is good. All right, you haven't finished project 1. You might have finished reading it, and you might have not. So the tutors will also kind of generally guide you about this project. So the projecty part of the project is really question 6. That's the last bit, which you need to kind of supply a 1 or 2 page report, which is kind of a standalone thing. The other questions build up to that in a sense. Okay, it's only question 6 also that deals with the long-term stationary behavior. The other questions are not. So that's your discrete time Markov chain project with some slight application to epidemiology. I must say that the relation to COVID-19 is only loose, okay? But it's not non-existent. There are students that finished on this course, later did an honors and then a PhD, and are now researchers in Australia and also elsewhere contributing to healthcare systems. So there is a real connection. Are there any questions about the project before I move on to the material? It might be a bit too quick, meaning that you've only gotten it yesterday. So it's any general questions about this? No? Okay. All right, let's get back to business. So we were here in SP1, reading through activity, what we call activity 2, I believe. And I want to actually go rather fast because I want to push on to activity 3 and then have you stop me where you see fit. So, for example, here we stopped with this theorem and its proof. And later I was asked, I think it was Nicholas that asked me a question in Piazza. So I'll just answer that now. Is that true, Nicholas? I think it was you. That asked me about, yeah, you confirm?
I asked you about like consult times.
Oh, okay, sorry, yeah. Oh, right, okay, thanks. Okay, so consult times, all right, so we got you, all right, so that's on Tuesdays, 2 to 4. If somebody can't make it Tuesday 2 to 4, is there anybody here already that knows that they can't make it? I mean, do you have a concrete clash with another bit stream coming into your living room? No, okay, so that's it. Okay, but you didn't ask that, so somebody else asked in PR about this inequality. in this proof. Let's just review very quickly what this is about. So we're saying if there is positive chance from going to x to y, but in addition, in addition, there is a non-certainty that will go from y back to x. Okay, so this is what I call this is positive chance. I'm speaking very loosely, and this is non-certainty, right? That will go back from y to x. Then x is transient. Okay, and the way this is done is by first of all just saying, well, if there is a way from going to x to y, then you're going to have some k, which is the smallest number of steps, just so we can quantify this path, this concrete path of length k, because we just want to write a mathematical expression. So there's a path of length k from x to y. Okay, and since it's positive, so so since this thing is less than 1, sorry, I'm touching with my arm here, then this thing is positive. Okay, and also this thing is positive, and hence this inequality holds. And the question was about this inequality, which I highlighted in yellow. So the thing is that the event tx equals infinity means we never make it back to x. Okay, that's what the event tx equals infinity under the condition that we start at x. Okay, that's how we read this event. This is we never make it back to x. Okay, so all you need to do to get this inequality is to say, let's look at all the sample paths that never put us back in x. There are all kinds of sample paths that don't put us back in x. Okay, there's not a unique sample path that doesn't put us back in x. Now, one specific sample path is this sample path here, which goes from x to y1, from y1 to y2, from y2 to y3, up to yk minus 1, and then to y. Okay, so it's a sample path from x to y, and then we end up not being back in x. Okay, so you can look at all the sample paths and say, treat the sample path that have the initial length of k steps that end up in y, and these are some of the sample paths that don't put us back in x. So the event described by this probability means not going back to x, but in a quite specific manner. And this means not going back to x in any manner. Hence, you could say this is like the event A, and here you're talking about the probability. So that's the probability of the event A, and that's the probability of the event B. But B is a subset of A. Okay, so B is a subset of A. Am I doing this correctly? No, B is a subset of A. Okay, sorry. Okay, so B is a subset of A. No, what am I doing? B is a subset of A. Okay, so hence the probability of A is greater or equal than the probability of B. That's all. Is that clear? All right, so let's just continue browsing through this, but I want to push forward to the next thing. But please stop me at any specific thing if in the reading you got stuck on that. Okay, so the next lemma says if x is recurrent, then that means that if x is recurrent and you can get from x to y with positive probability, then you must be getting back, okay? And that's just a consequence of this previous theorem, okay? Right, because otherwise this would be violated, okay? It all kinds of might make sense. And then is this example that we already spoke about, all right? And here they define, or the author defines a set as closed if it's impossible to get out of, i.e. if I is an A and you take some J that's not an A, then the probability from I to J is 0. Okay, probability of going from I to J is 0. Okay, it's a closed set. All right, and among the closed sets, then we need to say that a set is irreducible if whenever I, J is in B, then I communicates with J. Okay, so the irreducible sets are going to be these ones and these ones, and this is one and this is one for this example. And then comes the theorem that says if C is a finite closed and irreducible set, then all states in C are recurrent. Now this is what you might sometimes call a version of a nice Markov chain, and that's a very loose statement. There's not a real definition of a nice Markov chain. So you're speaking about a Markov chain, first of all, that has that's all the states are just going to be the state C, and then it's even finite, so you don't need to worry about issues dealing with infinite state spaces. And infinite state spaces are important, and often they're not. In our project, in all this assignment, all state spaces are finite. And it's closed and irreducible, so you can't actually worry about being stuck in some subset of states and some not. Okay, that would be a property of niceness. Another property of niceness would be that it's not periodic, and we'll get to periodicity later down. Okay, so in that case, all states are recurrent, and that means you're going to be on all the states you're revisiting infinitely often. You're coming to states again and again and again, even if the probabilities are low, you're coming to them. Okay, we spoke about this theorem, and I showed you a canonical decomposition. And then we're here. If X is recurrent and X, according to the wording of this book, communicates with Y, but let's say X leads to Y, then Y is also recurrent. Okay, and then a consequence of that is in a finite closed set, there has to be at least one recurrent state. Okay. Now that sounds a bit obvious. In a finite closed set, there has to be at least one recurrent state, but the example that we'll get to a bit later is going to be this one. So let me add a page here. And this is how often this is taught. And I'll get back to the simple random walk. Okay, this is 0, 1, 2, -1, -2. Okay, the simple random walk. Okay. Where you move here with probability P, and you move here with probability 1 minus P. You can call Q if you'd like. Okay, in this case, Q is the complement of P. Okay, so there's a single parameter P. And this thing continues forever, continues forever. So a simple random walk as a Markov chain, we can think of the simple random walk as a Markov chain. The transition probability matrix, and let me put quotes over the matrix, it's an infinite matrix. Okay, so it's not a finite matrix. You could still write it in one way or another. You'll put here like a 0, and you'll say this is a 0, and then you'll say I go from 0, 0 with probability 0, and I'm going to put a P here and a 1 minus P there. And then I'll put this is state 1, and this is state 1. This was -1. Okay, so this minus P, 1 minus P puts me at -1. P puts me at 1, right? And I have a P and a 0 and a 1 minus P. And you'll say that this band continues on forever, and this continues on forever, and this continues on forever, and this continues on forever. It's a transition probability quote matrix, infinite state space matrix. It's a Markov chain. Okay. So this is -1, -2. See what I'm doing? I mean, you often don't write it like this as a matrix, but you can view the matrix. Now, if you are doing anything, if you're kind of gonna, if you're truncating the state space, you say, okay, I'm only kind of living in this random walk in some finite set, then everything is finite and is fine. And then results such as this one saying, if you have a finite closed set, then there must be at least one recurrent state. But the thing is that here, you might have, in this infinite state space case, and we'll see this more in the other book, in the MC book, in the book of Norris, you might actually have that all states are recurrent or all states are transient. Okay, so even though you can walk in this walk, you can walk forward and back and forward and back and forward and back, it's actually, we're going to have enough results to soon see that if P equals half, then all states are recurrent. And if P is not equal to half, meaning that you're actually tending to move a bit more to the right or a bit more to the left, depending on if P is greater than half or less than half, then all states are transient. Okay, so that's kind of the typical infinite state space example to keep in mind, and this is not immediately obvious. Okay, and there are even nicer generalizations to this to random walk in the plane, where the same thing holds. But the interesting thing is that if you go from the plane to space, so if you actually, and then your state space is not just your location. If you're moving, like if you're doing a simple random walk on the line, your state space is location. If you're doing a simple random walk on the plane, it's harder to write the matrix, but you could still think about it as a Markov chain, then it's your location on the plane. If you're doing a random walk in space, so you can need your X, Y, and Z. So once you actually add the third coordinate in always, then everything's always going to be transient. So what's the meaning of this? Let's just understand the meaning. So with all states being recurrent, that actually means, and that turns out to be only in the case in half, that means that with probability 1, even if you have an excursion and you walk very far, you will return there. Okay, that's like, so think of this as being on a kind of an infinitely long road somewhere, say in Northern Territory. You know, this infinite long road in Northern Territory, and you walk left, you walk right, you walk left, you walk right. The state's recurrent, meaning that, well, you'll return back to any state with probability 1. It might take you a long time. On the plane, the same. But if you're actually a bird flying, then you're not going to return to a state with probability 1. Okay, and then that would be kind of a consequence. Okay, I'm kind of telling you about the future, but that's the main typical example, and that's also appearing in the MC1 book. We'll see it a bit soon, at some point. Questions? Very quiet class. You're not disrupting, not throwing anything, nothing. Did you guys just wake up? Is everybody like in bed with cereal or something? No comment. Okay, can only assume. Okay, has anybody gone to class from bed? Like, there's dead silence. Can you guys hear me? Maybe I've been speaking to myself for the last 15 minutes.
No, can hear you fine, Yoni. If you want some life, I'm taking a good break from work. So this is a good excuse to get a break from work. So thank you.
What's your work, Ashley?
I actually work at ComSec, so I oversee market risks in CBA.
Okay. Cool. All right. Thanks for taking a break from work. Okay, so you guys are there. Thank you. All right, you got some indication. All right, we're moving on to the next thing, which is this interesting random variable, n of y. I must say we're not going to use these things too much in the exercise, etc., but it's part of the theory. And maybe when we get to the problem set in the end of the course, right? So we have the two projects you'd see in the first project. We'll soon see the second one. We have time forward. Problem set in the end might have things related to this. But here I want you to kind of do this kind of crash course on Markov chains so you can move to the project. So n of y is an interesting random variable. It's a number of visits to state y. Okay? A number of visits to state y. All right? So it has a lot of implications, you know, the number of visits to state y ever. Okay? You can immediately expect that if a state is recurrent, the number of visits to it is going to be infinite. So here's a way to quantify n of y in terms of the row values. Now the row values are not, we still don't have an immediate way to compute the row values, right? Because the row values, I mean, we will through first step analysis, but at the moment we just assume these row values exist. Okay, so this says that E sub x n of y is row xy divided by 1 minus row yy. Now, what is this E sub x? E sub x, that is, you could read that as the, let me do a bit of erasing here. So that is the expectation of n of y, of the random variable n of y, given that x sub 0 equals state x. Okay. All right. Now, let's actually read this proof because it's instructive. But before that, let's just look at the expression. So this expression, you can also just read it and make some sense of it. You'll say, if you want to count how many times you are going to be in state Y and you started in state X, well, buddy, first of all, you need to make it to state Y. Okay, so making it to state Y is rho XY. Okay, it's not PXY, it's ever making it to state Y. And then what you're going to do is you're going to be in state Y a geometric number of times until you stop being in state Y. Okay. Now it might be that rho YY is 1. What does rho YY equal 1 tell us about state Y? What is this thing?
Well, it's recurrent. You always come back to it.
Right. So perfect. So if you always come back to it, then rho y1 is 1. That's the definition of recurrent. Thank you. Well done. And then you're doing here 1 minus 1. You're actually dividing by 0. Then this doesn't make sense. Okay. So, and then actually the expected value of y is of n of y is infinite. Okay. But if the state is transient, then what you're going to do is basically you're going to revisit state Y a geometric number of times. I mean, a geometric number, a random variable geometric number of times, and that is like the 1 over that is the expectation. So that's a bit just making sense of the expression, but let's just see the proof. So the proof, first of all, expects you to accept this beautiful fact. The moment, and you guys all know this. I mean, many people don't know this, but you guys know this, right? So it's just for any random variable x, you could look at the expectation as a sum of the tails, okay? I think this is in the old exercise sets before COVID-19 hit us in like exercise 2, in assignment 1, exercise 2 from last year. Maybe for continuous time random variables, but it's the same. Okay, so this is called the tail probability expectation. I mean, that's not typically how you think about expectation. I mean, typically you think about expectation when you just learn it, you'll say it's sum of k, p, x equaling. Now, how do I get rid of this thing? Sum of k, p, x. Let me write a bit nicer. Sum of k times the probability of x equaling k, right? That's what you mean by an expectation. K going 1 to infinity. You could say k equals 0, but then your first element here is going to be 0, so it doesn't matter. It dies, so just put a 1. Right, but that's a tail probability expectation. I think you've seen this before. You also prove at the bottom, Gemini says, yes, I agree, thanks. And this is actually just another nice simple proof of it, which I'll skip. Okay, so see yourself. Thank you. Okay. So it's describing the random variable x as a sum of indicators, but there are different ways to prove this. Okay. So that's an expectation of x, and they completed the bottom, as you say. Now the probability of returning at least k times, now you're kind of, our x is going to be n of y. That's our x, so you say n of 1. And returning at least k times is the same as the event that the first return time actually occurs in finite time. Okay. So then we say this thing, which is this thing, is now we're going to use 1,5, and let's go to 1,5 and remember what 1,5 was. It's equation 1,5, 1,4. Okay, so this was this equation that you return to y k times certainly is, right? So that's the kth return time is finite, is this px y times py y to the power k minus 1. So we stick this in here. The pxy is not a function of k, we take it out, and then we sum up the geometric series, and that's how we get this. Okay, it's kind of straightforward, but it's nice to have this expression. Now they're going to do this in a different way. Okay. So the different way is the expected number of returns to state Y is actually going to be a sum of Pn. Now remember, Pn is this thing is the x comma yth entry of the transition probability matrix raised to the power n. Okay. So for this is also, again, making use of indicators and saying the random variable n of y means that you're counting how many times. You're like looking at the realization. This is time n. You know, so you've got here, this is x0 and this is x1 and this is x2, and I'm now writing them like that, x3, say this is x4, this is x5, and this is x6, etc. And let's say that here, this is our state y. Let me write in a slightly more legible thing, y, okay? So this is state y. So the number of times we visit state y is just an indicator where we're summing up these indicators. So the indicators here were 0, 0, 0, 1, 0, 1, 0, 0, etc. Right? That's this representation. I mean, that's a very common trick in probability. And then if you take the expectation, now ideally, and in this case, this book glosses over it, you can put the expectation of an infinite series and put the expectation. Now, when we get to the MC6, which some of you might want to be reading anyway now, the appendix on probability on measure, then you'll see the conditions for when you can actually do this, okay? So a lot of, in the context of analysis that we do in Markov chains, a lot of the kind of the rigorization of things is saying, hey, let's not cut steps like the author did here. So what the author did here was move from this step. He stuck this summation inside, but the summation is an infinite series, and then did the expectation, wrote that this is the expectation of an indicator, which is fine. And the expectation of an indicator is a probability. But putting an expectation inside an infinite series often requires not often, always requires justification, which is the okay. If this was a finite sum, that's something else. But all the discussions we have here involve infinity. Okay, questions? All right. Now, then we get to a consequence is that a state is recurrent if and only if this series diverges. Okay. A state is recurrent if and only if the series diverges. Okay. And the proof immediately follows from what we had before. And this is often kind of a common condition for the infinite state space situation. So you look at just this yellow. So you wanna sum these things and see if this diverges or not. Okay, let me take you back now to this classic example, which I spoke about here, which will also appear later in the MC book. Sorry, this is so messy the way I'm writing. So if something's not, okay. I mean, when we used to meet face to face back in the good old days and breathe on each other, and you always told me, now nobody's complaining. I don't know why. Okay, so here you can actually, this is now the simple symmetric random walk on infinite state space. Okay, here you can actually compute P n x y. Okay. You can actually compute, you have an explicit expression to Pnxy, okay? And I'll leave this to you as an exercise to see what's the expression to Pnxy, okay? So let's just understand what that is. That's a probability that xn equals y, given that x0 equals x, okay? Let me simplify a bit and just go 0. 0, okay, 0, 0. So you can tell me what the n-step transition chance is from going to state 0 to going to state 0. Actually, you know what? Let's just do it. So we're starting now, let me choose a different color. I mean, the nice thing here is we have colors. So we're starting here, this is state 0 at time 0, and we're going to do n steps. We're going to do n steps. And we want to see what's the chance of being after n steps again at 0, okay? I mean, one thing you can do is you can take this infinite matrix, multiply it by itself n times, and give me the 0th row. Or exactly give me this element, but that's going to be complicated because working with infinite matrices, you can't do it in a computer system or something like that. But let's think elsewhere. Otherwise, what if n was 1? Is it possible in one step to go from 0 to 0? In one step, we can only be here or here, but we can't do that. Right? So for n equals 1, so this thing equals 0 for n equals 1, okay? If n equals 2, it's possible. If n equals 2, you'd need to move to the right and move left, or move to the left and move right, okay? And if n equals 3, it's again not possible. And if n equals 5, it's not possible. So in general, for odd n, you can't do it. This chain is actually periodic. That's a property called periodic. You can only return to certain states in certain multiples of times, okay? You don't certainly return, but you can, if you will return, you can only do it in certain multiples, okay? So let's instead, since we know that we're not caring about the odd numbers, and let me just make another page so it's so I have more space to work. Yeah, another page. Ah, this is a bug. This is a bug. So people should be fired. Okay, now it's okay. All right, so let's now then compute P2n by saying 2n 0, 0. Okay, so I mean after an even number of steps. Okay, so P2n 0, 0, which is the probability of x after an even number of steps being state 0, assuming that we started in state 0. Okay, so again, this is, let me put it up here. This is state 0, this is state 1, this is state 2, state -1, state -2, and we want after a tour of 2n steps, a tour of 2n steps, we're doing here, I'm doing 2n steps to return back to 0, okay? Or maybe the tour also, this is a different tour. The tour could have been like 0. Okay, so in those tours that return me back to 0 and are of lengths of 2n steps, how many steps were to the right and how many steps were to the left? Yeah, so a tour, this purple tour had 2n steps. This red tour had 2n steps and it put me back in 0. I mean, many tours will not put me back in 0. Tour, yeah, it's like a trip. Yeah, what we're not allowed to do these days, trips, okay? So, tour, this green step, 2n steps, back in 0. So that's again 2n steps. So how many of the steps moved to the right and how many moved to the left out of 2n steps?
Oh, so there has to be n to the right and n to the left.
Exactly. Well done, TJ. N to the right and n to the left. Okay. So out of the 2n steps, we had to have n to the right and n to the left. So why don't you just agree with me that then this is out of 2n, we need to choose n, p to the power n, 1 minus p to the power 2n minus n, which in my book is n. Okay. So I'm just going to write here. All right. So because the probability of this is like choosing from a binomial random variable, and binomials are very important for your homework one. I mean, it's all about binomials in a certain way. Okay. Out of the 2n coin flips, you had to choose n, and that would put you there. So the nice thing about the simple random walk is we can actually compute an explicit expression for the return probabilities. Now, let's go back to this theorem and see how this tells us something. A state is recurrent if and only if this thing diverges. Okay. So now, if this series diverges, okay, and now a bit of kind of an emotional thing. So in my world, diverging is bad. This is kind of how we're taught in calculus in the start, but recurrence is good. Okay, That's how you kind of taught in the third year course. So, you know, you're recurrent, you come again and again, diverging is bad. So one way to kind of remember this is if the diverging thing happens, then if the bad thing happens, you actually get the good thing. So I mean, this is, if you don't remember if this needs to be less than infinity or equal infinity, you just kind of remember it's the opposite from the, it's a good and bad mixed together. Maybe this is completely useless, but maybe after you think about it, it'll be a bit useful. So what we want to say is 0 is recurrent if and only if some n going from 0 to infinity of Pn00 equals infinity, or some n 0 to infinity of 2n over n Pn 1 minus p to the power n equals infinity. Okay. Now, it turns out, and this is details that I'll leave for you to look at, and we can speak about, ask me about it Tuesday if you didn't find out, then this only happens if p equals half. So what I'm saying is when p equals half, this series is going to diverge. This series is going to diverge, whereas when p does not equal half, then some n 0 to infinity 2n over n p to the power n 1 minus p to the power n is finite. Okay, and now this is kind of slightly beyond the core of what we need, but for this, what you'd want to do, does anybody have an idea of how to kind of see at all how such a series diverges or not? Okay, if this thing happens or this thing happens, if the yellow happens or the purple happens, I mean, the series involves binomial coefficients, right? Binomial coefficients are these kind of things, right? I mean, what's a binomial coefficient? It's 2n factorial divided by n factorial times 2n minus n factorial, which in my book is just n factorial, right? So this is 2n factorial divided by n factorial, okay? So how are you going to work with these? Well, the way that's presented here in MC1, let's move a bit forward. We're looking at MC1, the Norris book, the Markov chains, is this thing. What's this thing? Come on. No, it's not. It's not like in your bag of tricks, the Stirling's formula. So it's an approximation for n factorial, right? That's Stirling's formula. You've seen this before. Somebody's seen this before? I mean, you might not remember it if I wake you up in the middle of the night and say, "Hey, what's Stirling's formula?"
I've heard of it. I probably have seen it. I just don't remember it. I don't recognize it, but I recognize the name.
Fair enough. Good. Okay, that's all I want to know. Right, and you know, it's so a Stirling formula. It basically says that n factorial, which is like a product of 1, 2, 2, 2, up to n, is kind of like n to the power n, which you'd expect, right? But it's also multiplied by e to the minus n, and then there's also a n to the power half in there. Okay, so to actually see if this series diverges or not, in this example, the standard way is to actually replace this by Stirling's formula. Okay, so even though Stirling's formula is just an approximation, then that approximation is good enough to actually do the analysis of the series to see if it converges, yes or no. So it's getting to be very specific for that thing. And Matt Richards says, seen it in, hey Matt, in Math 4107, asymptotic analysis. That's with Tony Roberts, I assume. Right? I mean, yeah, Tony Roberts is like, you know, wake him up in the middle of the night, he'll, oh, Stirling will immediately tell you what it is. Okay, yeah. It is with Tony Roberts? Head of Math? Yeah, okay, right. Good. All right. So, I mean, the reason I spent a bit of time with this, because this is a kind of a classic example that spent a bit of time speaking to you about it now. It is a classic example where when you see this theorem, that's kind of the typical application for it. Okay. There aren't so many others. At least not kind of in typical applications, to see if a state is recurrent or not. But it's a characterization of recurrence or not. So when you get to infinite state spaces, these things become important. Okay, I'm going to skip these and have a quick look at what was in the self-study guide here. So we're in activity 2. So, you know, I suggested to do it twice. On the first read, skip the theorems, which is pretty much what I did with you, only speaking of the fifth theorems. On the second, read and rewrite to understand the theorems where available. Yes, so try to do that. And then let's have a quick look at MC1 section 1.3. Whenever I think of MC1, there used to be, back when I was your age, maybe, I don't know, your age is kind of a distribution. There was this guy called MC Hammer. Anybody know MC Hammer? I mean, he might still exist. I mean, I hope he didn't stop existing. MC Hammer? No? MC Hammer. Ned Lembrick knows him. Hi, Ned. Thanks for... Okay, Ned, share some videos of MC Hammer later on. He was, if I'm not mistaken, he was a Caucasian rapper. Is that correct? You can't touch this. Oscar Gibson. Okay, you can't touch this, right? He is that correct? He is like Caucasian rapper? Meaning, you know, I think so. Yeah. Okay. So, but this is MC Markov chains, not MC Hammer. Anything else in the chat? You can't touch this. No, that ends with Oscar. Thanks. Indeed, can't touch this. All right. All right. Hitting times and absorption probability, section 1.3. So this section takes us through similar types of principles. I already spent a bit of time here with you guys. And this example 131 is basically what with it repeats a type of analysis that we did in week 3 of semester. This is in a sense first step analysis. Okay, so in class we did it just for the probability of hitting stage 4, remember, of actually getting a reward. Okay, where ki is the expected time to reach here or here. Okay, so a here can be a set, and that set can be either a singleton or something bigger than one. And this is basically first step analysis. Now, it's summarized in this theorem, and I want us to read the statement in detail, and just I'll overview the 2 pieces of the proof. Okay, so this says in great generality. It says, you want the vector of hitting probabilities, HA, for some set A. So you give me some subset of the state space. And by the way, this book of Norris, the MC book, MC Hammer, it speaks about infinite state space from the go, right? So there's not, unless there's a specification, everything is kind of infinite state space, countably infinite. Okay. So you've got this, he calls this a vector, but this doesn't have to be a finite vector because the state space here might be infinite. So it's a collection of probabilities where if you start in state I, where I is some element of the state space, what is the chance of actually hitting state A? Okay. By the way, what's going to be that chance if all the states in A are recurrent? What's going to be HIA if all the states in the set A are recurrent and also I is an element of the same class of A? There's going to be 1, right? So sometimes this is not an interesting question. Sometimes you'll hit it with probability 1. Okay, the questions are interesting when this question is interesting when you don't hit it with probability 1. Okay, now the way they write it is they say it's the minimal non-negative, we'll see what that means in a second, to the system of linear equations. Okay, and this is how they specify the system. So it's not specified directly as a matrix, but it's all we have are linear relationships between different elements of these vectors, and hence it's a system of linear equations. So first of all, for I in A, what you're going to get is HIA is going to be 1, because you've already started, so you've hit from the go. Again, hitting here in this book, hitting is the infimum is going from 0. Okay, so you start in the state, you've immediately hit it. And then the important first step analysis equation is, and let's read this, the chance of hitting A going in state I is, let's look at the intermediate first steps J. Yeah, oops, I just killed this J. All right, these J's, okay, the intermediate first step J's, of making a transition to J, from I to J, okay, that's this transition from I to J, this transition from I to J. And then let's restart the situation and ask what's the chance of hitting J. That's all. Okay, so it's just first step analysis formalized. However, by minimality, what they mean is that if you have some other solution to this system of equations, okay, because this system of equations is not guaranteed to have kind of a unique solution. So if you have another solution that's non-negative, okay, if the solution has negative elements, it doesn't matter, then HI is going to be, the actual probabilities are going to be less than or equal to the elements of that solution for all I. Okay, that means if you're in a situation where there are actually multiple solutions to this linear system of equations that are non-negative, which can be the case, okay, then choose a minimal one. So the first part of the proof does, and I'll let you read this yourself, so does first step analysis. Okay, first step conditioning, I mean, we're conditioning here on x1, okay? We're conditioning on x1. Okay, and remember that if we have I here, what we mean, that I actually means that we also have here an x0 equals I. All right? And we're doing that conditioning and getting these equations. The second part of the proof speaks about the minimality. And just spend a bit of time reading that as well. And it says, let's say you have a different solution, x, okay? Then we'll see that it must be that x is an upper bound, and that xi is an upper bound to hi. This is kind of reminiscent. We had this one proof when we spoke about branching processes back in the days, where we looked at the minimal solution to the probability generating function of the offspring distribution hitting the identity line, right? And also the minimality was kind of proved in a similar way. So it's not critical, but you could read this. Now, this minimality, why is it needed? Why do we need it in practice, or etc.? And when we're not going to use this type of thing in our project and things like that. So if we go back here to the random, the gambler's ruin, okay, so that's the gambler's ruin example, which they have up here. Okay, when we together spend time in class in the gambler's ruin, we also put a condition, and let's say we are now looking for KI4. Okay, that's a chance of winning. You see, I put here 4 as a set. It's the singleton set 4. We also in class we said KI4. We said K14. We impose that condition equals 0. Okay. And that was used to prove things, okay? So we imposed this condition class because we knew that if we hit 1, we're never going to hit 4, okay? Sorry, let's not do K, H, probability, H, okay? However, these equations don't tell us anything about this, H1, 4 equals 0. So if we don't impose them and we write a system of equations, then we're still missing the H1 equaling 0 condition. And then so you have here kind of a whole bunch of solutions. You have here, sorry, a whole bunch of solutions. But with H1 equaling 0, you know that you need the minimal one, okay? But that's not really, so that's how the minimality, this is a bit of a subtle issue, okay? And it's not core. That's how the minimality, the minimality plays a role here. Where it does become important is when you speak about infinite state spaces, okay? And we won't go into this with detail, but you could skim this to kind of get the general gist. So this is the infinite gambler's rule. It says, I'll go on for another 5 minutes if you guys don't mind. It says, consider the Markov chain, because we need to finish now. Consider the Markov chain with a diagram, and this thing kind of goes on forever. You see from 0 on. So this gambler, you know, it's this is kind of maybe the, you know, the hardcore gambler, right? The guy doesn't stop, right? He only stops when he hits 0. Okay, so this is a specification of the transition probability kernel, right? P00 equals 1, and then you go to the right with P and to the left with Q. Okay, so when you write the system of equations here, it's an infinite system of equations. Actually using the minimality condition is important. Similarly, for this birth-death chain, a birth-death chain is birth-death processes, we'll speak about them more later on, are in general very important processes where you just move either to the right or to the left, or to the right or to the left, but with arbitrary probabilities which are state-dependent, Qi and Pi. So these are rather involved, but they involve the minimality solution. Just I'll just mention this without saying much more about it. The analogy from going to H's is K's, and K's are for the mean terms, okay? And you get the similar type of system of equations, but with this one also do the first step analysis. So again, if you quickly look at the proof here, then this is the first step analysis, and this is a minimality. First step analysis, this is minimality. Okay. Up to him. All right, I hope this finishes for us. I wanted to finish today. That finishes for us activity 2. Of course, spend some time on it yourself, but now you can also do it in view of where you need to be here carrying out project 1. So many of the things you're doing in activity 1 and activity 2 do not directly help you for project 1. Let me say something quickly about project 1. So activity 5, so feel free to kind of push just a bit forward to activity 5. Because activity, you already have enough of the Markov chain background to do most of project 1. You just need to start doing activity 5, okay? So first of all, this is a bit general. Read EM4 stochastic models in discrete time. I should refine that. I'll make an update to the activity. You don't need to do that. You just need to read the first 2 sections of stochastic models in discrete time. But I also recommend, as I said in the project description, I also recommend that you, where is it? How do I go there? No. I also, in the project description, that you spend time reading section 1.4 from the introduction chapter. Okay, I sent you that introduction chapter at the end of Paul's week. So all of this project, it'll take you a bit of time. You'll speak about it with the tutors. Some of you are starting tutorial in a minute, okay? All of this project, you pretty much have the knowledge of what you need to do there from a Markov chain perspective, with the exception of the actual concrete part, which is 6, okay? Where you need to deal with stationary distributions. And stationary distributions are where I'll pick up next Tuesday, and that's basically activity 3. Okay, moving on to activity 4. Any questions before we wrap up? Okay, well, let me wish you a good weekend. Again, be easy on yourself in these hard times, but still demand from yourself to progress on work. It is what it is. Write me if you need anything specific, special. All right, have a good weekend. Bye.
Thanks, Yoni.
Bye, yeah, thanks.
See ya.
Bye. Bye-bye.